Hello, I'm Walker Rowe. You look at the media reports on data center growth. People in the United States, around the world, are complaining about data centers growing and they're using too much electricity. Electricity bills are going up. And then the journalists try to explain what's going on. They say the assumption is that data centers are growing because they have more customers, more people using Chat GPT. But what's really interesting is it has nothing to do with adding people. It has to do with making models larger. Now I'm going to give a technical description here, made as non-technical as possible, of what actually causes data center growth. And you will be quite surprised to find out it's simple arithmetic. It's matrix multiplication. It's linear algebra. There's this rule that we'll talk about. It's called the chinchilla law. That says when you add more data to a training model, you need to add more parameters. The model needs to grow in size. Otherwise, this thing called loss in compute get out of proportion and the model will not perform correctly. So think of it like this. It's like you have one computer and it does okay. So you need to add two computers. It does a little better. That's a linear growth. But because of this need to keep these models in balance, we have geometric growth. Geometric growth means you have 1, you have 2, you have 4, you have 8, you have 16. And that's why these things are spreading like, as we say in America, mushrooms after a spring rain. So anyway, I'm going to walk you through the basic mechanics of this from a technical point of view. I'll talk about basic linear algebra, talk about parameters, weights and biases of deep learning neural networks, word embedding, tokens, and then explain to you how these basic steps work. And then you can kind of see for yourself how you grow a data center simply by adding GPUs to keep up with the enormous increase in matrix size that arises from all this multiplication. It's just math. It's quite interesting. I hope you'll enjoy this. When we talk about AI models, large language models, we generally talk in terms of number of parameters. Gives you an idea how large it is. The larger it is, the more it can learn, the more complex reasoning it can do. So for example, the bottom end of the size, something you maybe could even run on your own computer using a model like Ollama, which I have on my computer, I have downloaded. We just have, say, 1 billion parameters. We'll talk about what a parameter is. 4 to 8 tokens in one GPU. Went up considerably in size. Medium model would be one of the hosted models hosted in the data center of the AI company, would be, say, 7 billion parameters. We'll see what parameters is, but basically it's the weights and biases. So 7 billion of those, 1 trillion tokens, trained on 1 trillion tokens, or you could say words, bits of text, 64 to 128 GPUs, using 128 gigabytes of training virtual memory. And it takes weeks to train that. And going up to the large models, we see that it can take months to train. You know, in Chat GPT version, what was it? It was 3.1. The first one that came out in a couple years ago in December, it had been trained for like 10 months. Now things have changed. It takes only a couple of months. Plus they have lots of different models that they're working with that take different amounts of time. But anyway, so it's this is what we're going to be talking about, why this drives data center growth, not necessarily consumer demand or the number of people using it. Okay, so you need to, let's give you a background here. Basic, bare minimum overview of what training a AI model means. It's not complicated, or we will keep it not complicated. So first we just remember from high school algebra the basic equation for a line. Y equals mx plus b. Okay, AI is not really much more complicated than that. It's you'd be quite surprised at how simple the basic math is. It's just larger than that. Okay, in this example, what varies in this formula to determine y, which we, in terms of AI, we would call the prediction, is m, which in math means the y-intercept, but in AI we call that weights, and then biases. So the training step calculates the optimal weight and bias to reduce the error. The error means the difference between the prediction and the observed value. Now, looking at this slide, this is what happens when you stack a bunch of these equations on top of each other. You get multiple weights. Like this one is, the top one is basically a 3x3 matrix of weights, and then one layer in a neural network with 3 nodes, x1, x2, x3. Then you calculate that using matrix multiplication, which is where GPUs shine. This is what they're for. Then you add to it biases. In this case, the bias is a vector of 3 of them. And that will give you y, the prediction. So can you see that's basically the same formula, just larger, a lot larger. Okay, now here's what one neuron does. Okay, all of this is the same thing. It's just taking inputs x1, x2, x3. Okay, it then calculates weights iteratively and biases by running it through this little sigma symbol. It means an activation function. And then the output is a prediction. You know, large language models basically are really predictive models. So this thing runs over and over. This is one little neuron. Now in that billion parameter large language model, the number of layers and neurons, of course, would be much larger. We're going to talk exactly about that. This size is what's driving growth. Now here's a neural network. We have inputs x1, x2, x3. These lines mean the connections between the data and the neurons. These are called hidden layers. The circles are called neurons. For each one of these, just remember, we do that matrix multiplication over and over in a continuous loop until we tell it to stop. We tell it to stop when it reaches the accuracy that we want. Now, I like this graphic here a lot. I don't know who made it, so I can give them credit. I found it, I think someone had copied it onto a website. But this is a moving image that it shows up, okay, you start off with inputs 1, 2, 2.1, 1.2, and then the weights go down and the biases go down until the model converges. In other words, until you get the optimal result. And as you can see, it runs over a period of time. It runs until you get the minimum loss. This is how AI works. It's how most machine learning models work. There are other types of AI than the neural networks. Okay, here is this bold looking thing is the loss function. Loss function is how we tell how close our prediction is to what we calculate. And remember that data is labeled. So we have some input and a label. So that says, okay, we expect the output of this model to be this value. Okay, the difference between that value and what we get is the loss. Now, in terms of language, these are language models. These words are encoded into numbers, and the loss, for example, in this chart, is the bottom. We look for a minimum, is the difference between the predicted value and the observed value, and given the weights and biases that we have now calculated. Okay, now the hardware, the GPU. Okay, the GPU is it's really designed to do one thing: matrix multiplication. And to me, that's quite remarkable that we've built data centers all over the planet simply to do, which is not a very complicated math operation. It's just large because of the exponential growth in numbers. So here's NVIDIA's top of the line card. It's called the NVIDIA H200 NVL. Okay, it supports 456 tensor cores. Tensor core is where matrix multiplication takes place. Now, if we talk about performance, okay, CUDA is the programming language that NVIDIA wrote that lets these operations happen in parallel. You know, computer code is not in parallel. A CPU on a computer, through time slicing, sends the same instructions through the computer one after another. Okay, it looks like many things are going on at once when you click your mouse or you watch a video or something, but it's all running through the CPU. So the GPU is quite different. It just says, let's do everything at once, go. Because order doesn't matter. You'll see that matrix multiplication is not linear. Things can happen all at the same time. Now this performance here is written as TFLOPS, TensorFlow operations per second, or trillions of TensorFlow operations per second. Now it's worked out. If you deal with programming, you don't usually think about numbers. You say that's an integer, that's a decimal number. But when you're dealing with large amounts of data, you think of precision. So this is talking about three different numbers. We have 64-bit numbers, 32-bit, and 8-bit. A bit means how long it is. For example, the 8-bit number, the largest 8-bit number you can have is 255. The largest 64-bit number you can have is, I don't know, it's very large. I think it's 2 raised to the exponent 64. 2 raised to the exponent 8, I think it's 256. Need to check that. But look at this. Just by making the numbers smaller, the performance increases astronomically, right? Something that normal programmers don't think about, but CUDA programmers have to think about: the precision or size of numbers in bits. Okay, this card has 141 gigabytes of memory. That's a lot, you know. For the machine learning model to work, it has to have all of its data held in memory at that you know, pretty much in perpetuity. It's not like you read data off the disk and then do your calculation. No, it's like a living thing that's up there in scope, ready to go when we need it. Okay, here's another graphic, just explains that one flop is 10 to the 12th floating point operations per second. Floating point number is just a decimal number. By the way, the person who figured out how to represent those in the computer was none other than Alan Turing. Can I hear? The last thing we have to cover is matrix multiplication. Now this might look a little bit nerdy, a little bit boring, or even complicated, but it's not. Just think of it. It's just multiplication of two matrices. Remember, matrices is that y equals mx plus b formula, but here we're multiplying mx, and they are matrices or vectors. A vector means a matrix of one dimension. Here we have two 3x3 matrices, two matrices with 3 elements and 3 dimensions. So the first thing that we do is, okay, multiply everything by everything else. So on the left, we will break up this into 3 rows, the pink one, blue one, and the green one. On the right, we'll break it up into 3 columns. As you take the row on the left and multiply it by the column on the right. Okay, so now we're going to do our first operation. We're going to take 1, 2, and 3 and multiply it times each of these columns, pink, blue, and green, which are these floating point operations. Here we have these floating point operations. Each of these numbers, now here these are integers, but AI models work with decimal numbers, 0.0 something like this. So we have this many decimal numbers. So we multiply each row and column cell and save that result and then sum it. This is called the dot product. And then we do it for the next row, next set of columns, and then we do it, that's the blue one, then we work on the green one, and then we get all the numbers added up, and we have the final resulting matrix. Okay, a 3x3 matrix multiplied by a 3x3 matrix is going to be a 3x3 matrix. So that's the mechanics of floating point operation. It's the basic simple math function that is the reason that GPUs exist. Because as we just showed you, these are 3 separate distinct things. Each one goes off and multiplies, gets its sum, then it can go off by itself, do that, and come back together and fetch the sum and hand it back off to whatever step called it. So you can see that this can be done on separate GPUs. There's a bit of a ridiculous situation here. It's driving data center growth. The rule for best performance says if you want to keep the loss low, then you need to grow data and parameters at the same speed. So what that means is now we have the situation where AI companies have grown their models as so many parameters, they're running out of data to feed into it. So basically, if you added just data to an AI model, then it would grow proportionally. But there's this thing called the chinchilla rule, which basically says that if you add data, you also need to add parameters to keep the loss predictable. Okay, what is loss? Loss means the difference between your prediction and the actual outcome. When you're running a large language model and it says something, that data has been labeled so that what it says is a prediction. Like if you ask it to write something, and then what it writes is totally absurd, then there's a large loss, because mathematically there's a large difference between what it should have said and what it did say, based upon trained data that has been labeled. We kind of need to break this down. Okay, there's this idea of a flop, and I just showed you basic matrix multiplication. How many flops it took to multiply two matrices. Each flop is a single floating point arithmetic operation, like addition, subtraction, multiplication, or division. Floating point numbers just mean decimal numbers. Okay, parameter now, as we looked at and we'll look at again, is one learnable weight or bias in the neural network. You remember in the example that we gave, we started off with our high school algebra. Y equals mx plus b, which is just the slope of a line. Well, m, in math it's called the y-intercept, but in machine learning we call that the weights. B is the bias. So basically it's like a big algebraic expression, except with billions of parameters, meaning billions of these weights and biases. The x in this example would be the input. The input is word embedding. What is word embedding? Well, okay, so you need to understand what a token is. A token is input text after it's been broken up by the tokenizer. A tokenizer is a way to take text and turn it into numbers. Okay, flops, the required number of operations, floating point operations, is proportional to the number of parameters in the model and number of data tokens that you train on. Now, as I said, the law says, best practices says these two things should grow together to keep the loss low. Basically, you could say that that's so that we don't have a model that's either wrong or that is not capable of learning complex relationships. Okay, word embedding is a symbol or for one chunk of data. For example, it's like a number, an index pointing to a vector, and then the word embedding itself is a vector representation of that token. Okay, if you keep the architecture fixed and just add data, it grows linearly, not exponentially. Okay, if you keep the model size fixed and add more tokens, training flops grows roughly in direct proportion to tokens. If you double the data set, you double the compute. Again, linear growth. That doesn't explain why data centers are spreading geometrically across America and other countries. All right, the chinchilla style scaling law says to use your compute efficiently. Efficiently here, they mean not necessarily speed or anything. It means with a predictable loss, you should scale parameters and tokens together. Roughly keeping, they've got a number here, tokens roughly equal 20 times the parameters. So when you increase your parameters by 10, You also grow the tokens, which makes total training growth like so. AI companies don't want their training model to take years. A GPT-3 class runs at 10 to the 11 power parameters. That's the order of 10 to the 23 flops. That's an enormous number. One GPU would take centuries to calculate that. So they scaled to thousands or tens of thousands of GPUs to finish in weeks or months. So the seemingly exponential growth in data centers comes from increased model size, more parameters, increased data size to keep the compute optimal, and keeping training size roughly constant, weeks, not years, which forces huge parallels of GPU clusters, which means more data centers.